Section: Introduction. In this section, we discuss the advancements in next token prediction, which have transformed language models and led to innovations like ChatGPT, raising questions about the emergence of artificial general intelligence, AGI. However, we find that its application in multimodal models is still uncertain, with little evidence of its effectiveness across various tasks. In multimodal contexts, complex diffusion models have dominated vision generation, while vision language tasks have been primarily addressed by compositional methods like CLIP combined with large language models, LLMs. Despite initial attempts to merge generation and perception, such as Emu and Chameleon, these approaches either connect LLMs with diffusion models or do not perform as well as specialized methods. In our work, we introduce Emu3, a new set of advanced multimodal models that rely exclusively on next token prediction, removing the need for diffusion or compositional techniques. We convert images, text, and videos into a discrete format and train a single transformer model from scratch on a variety of multimodal sequences. Emu3 achieves top performance compared to established task-specific models in both generation and perception tasks. It surpasses the leading Stable Diffusion Model, SDXL, in human evaluations and public benchmarks like MSCOC030K and GenEval. For vision language understanding, Emu3 competes effectively with the well-known LLAVA 1.6 model across several public benchmarks. Additionally, Emu3 can generate videos. Unlike Sora, which uses a video diffusion model, Emu3 generates videos by predicting the next token in a sequence. It can simulate aspects of real-world environments, people, and animals, extending video content based on user prompts to create high-quality videos. Emu3 also competes with other video diffusion models on the VBench benchmark for text-to-video generation. We are making key techniques and models available to support future research. Notably, we provide a robust vision tokenizer that converts videos and images into discrete tokens, which was not previously accessible. We also show that the next token prediction framework can effectively incorporate direct preference optimization, DPO, to align the model with human preferences. Our findings strongly suggest that next token prediction is a powerful approach for multimodal models, extending beyond language models and achieving state-of-the-art results across various multimodal tasks. By simplifying complex designs and focusing on tokens, we unlock significant potential for scaling during both training and inference, indicating that next token prediction could pave the way for developing general multimodal intelligence. Regarding our approach, we train Emu3 from scratch using a mix of language, image, and video data. For language data, we utilize a high-quality corpus of both Chinese and English, similar to what was used in Aquila. For image data, we compile a large-scale dataset from open-source web data, AI-generated content, and high-quality in-house sources. Our filtering process includes several key steps. We discard images with resolutions below 512 by 512 pixels, assess aesthetic quality using the Layon AI aesthetic predictor, and apply text detection and color filtering to retain only relevant images. We also prepare additional data for image understanding by extracting millions of representative images from diverse sources. To annotate our filtered dataset, we develop an image captioning model based on Emu2, generating around 1 million image caption pairs with the help of GPT-4v. For video data, we gather a wide range of videos and pre-process them through a 4-stage pipeline, which includes scene splitting, text detection, motion analysis, and aesthetic quality assessment. We caption the filtered video clips using a video captioner trained on our image captioner, with the initial labeling done by GPT-4v. For efficient large-scale deployment, we use VLLM to speed up the captioning process, ensuring that both short and long clips are effectively captioned. Section Summary. In this section, we introduce Emu3, a state-of-the-art multimodal model that utilizes next token prediction for generating and understanding images, text, and videos, outperforming existing task-specific models. We detail our comprehensive data collection and processing methods for training, which include high-quality language, image, and video datasets, ensuring robust performance across various multimodal tasks. Section: Vision Tokenizer. In this section, we describe our Vision Tokenizer, which we train using SBER-MO-VQGAN. This tokenizer can convert a video clip sized 4 by 512 by 512 or a 512 by 512 image into 4,096 discrete tokens from a codebook of 32,768. We achieve a 4-fold compression in the time dimension and an 8 by 8 compression in the spatial dimension, making it adaptable to various resolutions. By building on the MO-VQGAN architecture, we add 2 temporal residual layers with 3D convolution kernels to both the encoder and decoder to improve video tokenization. We train the tokenizer end-to-end on the LAION high-resolution image dataset and the intern-vid video dataset, using a combination of loss functions, including L2 loss, LPIPS perceptual loss, GON loss, and commitment loss. We present qualitative results in our figures and report metrics like LPIPS, PSNR, and SSIM scores using an evaluation dataset of 3,172 videos from Pexels. The videos are reconstructed over 5 seconds while keeping the aspect ratio intact. During evaluation, we resize and crop the original and reconstructed videos based on the shorter side and sample 8 frames at 12 frames per second. For our Emu3 model, we maintain the structure of established large language models, like Llama 2, but expand the embedding layer to include discrete vision tokens. We use RMS norm for normalization, GQA for attention, and the SWI glue activation function, while removing biases in certain layers. We also implement a dropout rate of 0.1 for better training stability and use the Quen tokenizer for multilingual text tokenization. In the pre-training phase, we define a multimodal data format that integrates textual information for image and video generation. We resize images and videos to maintain an area close to 512 by 512 and generate vision tokens. We introduce 5 special tokens to combine text and vision data, structuring our training data to include various elements like caption text and meta text, which contains resolution and duration information. Our training objective focuses on predicting the next token using standard cross-entropy loss, applying a weight to the loss for vision tokens to prevent them from dominating the learning process. We utilize a long context length during pre-training to manage video data and employ tensor, context, and data parallelism to maximize computational efficiency. The pre-training occurs in 2 stages, starting with text and image data and later incorporating video data, both using a learning rate that gradually decreases. After pre-training, we conduct quality fine-tuning to improve the outputs for vision generation tasks. We continue training with high-quality data, focusing on vision tokens and increasing the resolution of training data. For video data, we apply strict quality filters. We also implement direct preference optimization, DPO, to align our model with human preferences, constructing our dataset through a series of evaluations and selections based on user feedback. This approach helps us refine our model further by minimizing losses associated with DPO and next token predictions. Section Summary. In this section, we describe our Vision Tokenizer, which encodes images and video clips into discrete tokens with significant compression and is trained using a combination of loss functions on large datasets. We also outline the architecture and training process of the Emu3 model, emphasizing its integration of text and vision data for improved multimodal generation and alignment with human preferences through direct preference optimization. Section: Vision Language Understanding. In this section, we describe our approach to vision language understanding, which involves a 2-stage post-training process. First, we conduct image-to-text training, where we combine image understanding data with pure language data, ignoring losses related to vision tokens for text-only predictions. We resize each image to about 512 by 512 pixels while maintaining the original aspect ratio. In the second stage, we sample question-answer pairs to improve our model's ability to follow visual instructions. Images smaller than 512 by 512 or larger than 1024 by 1024 are resized to fit these limits, while others keep their original size. Next, we evaluate the performance of our model, Emu3, using automated metrics on well-known text-to-image benchmarks like MSCOC030K, Gen-Eval, T2I CompBench, and DPG-Bench. Our results show that Emu3 outperforms autoregressive diffusion methods in aligning images with text and is competitive with leading diffusion-based models, even without using pre-trained language models. We also report results from Gen-Eval and T2I CompBench after expanding short prompts with a rewriter. Emu3 performs better in dense captioning due to its use of synthetic labels during training, although the brief evaluation prompts in these benchmarks may not fully capture the model's capabilities. Following the approach of DAL-E3, we also use GPT-4v as a rewriter for our evaluations. Our findings indicate that Emu3 significantly surpasses Chameleon, a multimodal autoregressive model, and the latest autoregressive diffusion methods, Show-O and transfusion. It also outperforms SDXL and matches the performance of top diffusion models like DAL-E3. We provide detailed comparisons in the appendix, including results from original prompts. To further evaluate text-to-image methods, especially diffusion models, we assess how well-generated images align with text conditions using T2I CompBench, where Emu3 shows competitive performance. We also compare our models on the DPG bench, which uses longer prompts with more detail. Emu3 DPO achieves an overall score of 81.6, surpassing SDXL and PixArt Alpha, and is comparable to DAL-E3, demonstrating its ability to handle long prompts. However, we notice a slight drop in evaluation results when comparing Emu3 with Emu3 DPO, possibly due to the DPO datasets focusing on aesthetic quality, which differs from the automated evaluation models. Therefore, we incorporate human evaluation. In our human evaluation, we compare the text-to-image generation abilities of different models using a set of 100 diverse user prompts, evaluated by 3 independent voters. We focus on visual quality and prompt adherence, presenting a weighted score for overall performance. Our results show that Emu3 outperforms SDXL and is on par with DAL-E3 and MJV 5.2. We also illustrate how DPO fine-tuning enhances visual quality and prompt following. We showcase 25 images generated by Emu3 to highlight its capabilities, noting its flexibility in resolutions, aspect ratios, and styles. For video generation, Emu3 can create 5-second videos at 24 frames per second and can be extended indefinitely using an autoregressive method. We present qualitative examples of video generation, including 6 frames from the first 3 seconds. We quantitatively compare Emu3 with 13 leading text-to-video models using VBench, a toolkit that evaluates video generation across 16 dimensions. While Emu3, as an autoregressive model, does not match the most advanced proprietary models like Kling and GEN3, it outperforms most open-source text-to-video models, showcasing its strong video generation capabilities. Section Summary. In this section, we describe our 2-stage post-training process for vision language understanding, which includes image-to-text training and instruction tuning, leading to enhanced performance in text-to-image generation. We also present our evaluation results, showing that Emu3 outperforms several state-of-the-art models in both automated and human assessments, and demonstrate its competitive capabilities in video generation compared to other leading models. Section: Future Prediction. In this section, we discuss how Emu3 can extend videos by predicting future frames. We provide examples of video extension, where we take 2-second videos at 24 frames per second and break them down into discrete vision tokens for context. Emu3 then predicts the next 2 seconds of content in the same token format, which can be converted back into videos. Our findings show that using next token prediction allows us to extend videos temporally, accurately predicting actions of humans and animals, their interactions, and changes in 3-dimensional animations. We have successfully extended video frames by 8 seconds using just 2 seconds of initial video data. Next, we evaluate Emu3's vision language understanding by testing it on various public benchmarks. Our results, which we detail in our tables, compare two types of methods: those using pre-trained clip vision encoders and those that do not. Emu3, as a purely encoder-free method, outperforms its competitors on several benchmarks without relying on specialized pre-trained language models or clip, highlighting its strong capabilities in multimodal understanding. In the related work section, we note that clip learns versatile vision representations through contrastive learning on large image text pairs, achieving notable results in image classification. Flamingo connects pre-trained language models with vision encoders like clip, showing promising few-shot multimodal understanding. The rise of large language models has led to a trend of combining pre-trained vision encoders with these models, resulting in effective vision language models like the Blip series, Mini GPT-4, and LLAVA, which have shown improved performance through curated datasets and training strategies. While some models, like Fuyu and Eve, use encoder-free architectures, they still struggle to compete with top-performing vision language models. Emu3 is the first to show that a decoder-only model trained on next token prediction can achieve comparable or even superior performance to encoder-based models, paving the way for advancements in this architecture. In vision generation, diffusion models have recently excelled in creating high-resolution images. The release of the Stable Diffusion series has spurred significant research in this area. Other approaches, like DAL-E and Video GPT, generate images by predicting the next token in a sequence. However, these methods often do not match the performance of diffusion models or rely on complex frameworks. Emu3 demonstrates state-of-the-art capabilities in image and video generation using a single transformer decoder, and we are committed to open sourcing our work to encourage further research. Lastly, we highlight early efforts to unify vision understanding and generation, exploring various generative objectives. Emu and Emu2 introduced a unified autoregressive objective for predicting the next multimodal element. Recent methods have attempted to combine diffusion and autoregressive techniques, but they still lag behind specialized architectures like SDXL and LLAVA 1.6. Emu3 uniquely shows that next token prediction across images, video, and text can outperform these established models without relying on complex methods.